This is a video of the workshop regression in SPSS. We cover 3 types of regression in this: simple, multiple and logistic. If you looked at our video ANOVAs in SPSS, we talked about some statistical concepts such as alpha levels, type 1 and type 2 errors and power, and we give you some examples of those in this workshop. We also have a quick word on research and more complex statistical tests in SPSS. So the way that we've structured this workshop is that we've based it on the most common queries we get into the Math Skills Centre. And what we want you to get from this workshop is not just how to run the test in SPSS, such as what menus to go to, but we want you to actually understand what the test is doing and what the output means. So this is just an introduction. It's likely that you'll need to study further if you're doing one of these regressions, especially if you're doing logistic regression. So just be prepared for that. And just to say, all the data we use in this workshop is fake, so don't take any conclusions from the results. So let's start with simple linear regression. Some people will call this just linear regression. The simple part refers to the fact that we've only got one independent variable, and the linear part is referring to the fact that the relationship between the dependent and independent, the relationship between the two variables, is roughly a straight line. And this is usually done between 2 scale variables. So scale is the same as continuous, it's a type of data. But not always there. Some people do put ordinal data into a linear regression. So let's get some data to play with. If you go to the VLE where you're watching this video and open up workshop data, exam grade simple regression. And the research question that this data is addressing is, can hours of study, as in the number of hours that a student said they've studied a subject for, can that predict the exam grade? And that's important in regression. We always have an independent that is predicting the dependent. If you're just looking for a correlation, then you shouldn't be using regression, you should be using correlation. So let's go to the VLE and open up that data set. You can do this at the same time, or you can just watch the video, it's up to you. So here's the first column, which is our independent, the hours of study. And then in the second column, we've got our dependent variable. What we're going to do in SPSS is check for assumptions and then run the test and look at the output. So the first assumption for regression, so remember we have to check assumptions to make sure that our data is suitable for that test, otherwise the answer isn't reliable. So the first assumption is that we've got linearity between the 2 variables. So we're going to check that using the chart builder in SPSS. Then we're going to run the regression. And at the same time as running the regression, we're going to check for 2 other assumptions. So once we've run the regression, we look at the output and we can check to see if we've got the assumption of normality for the residuals. So if these are new concepts or new words to you, don't worry, we're going to explain them. And the third assumption we're going to check is this, homoscedasticity. So let's explain what residuals and homoscedasticity is. The simplest definition for residuals is that it's the difference between the observed, so these dots, and the predicted, so this line, for each of the data points. So the residuals are represented in this graph by the red lines. So all this is a graph of our independent on the x-axis, so that's the number of hours students reported studying, and the final exam score on the y-axis. And then we've got this line of best fit running through it. That's the regression. And then each one of these is a person. And you can see that some values are right on the line and they'll have no residuals. Like, so this will probably be 0. This will maybe be, I don't know, 1 or 2, very, very small. And then we've got some that are very, very far away from the line. So this one and this one, they have quite big residuals. But the majority of the residuals are, let's say, a medium distance, maybe, I don't know, 10, 15 units away from the line. So if we plotted these values, of the red line values, we would get very few that are right on the line, very few that are very, very, very far away from the line, and the majority would be a medium distance. And so we'd end up with a bell-shaped curve if we did a frequency of them. So that's what we mean by residuals. The other assumption, homoscedasticity, you can think of this as the same as equal variance. So if you came across equal variance, which in a t-test maybe, and that's where we're making sure that the spread of the data in one group is roughly the same as the spread of the data in another group. In a regression test, people don't call it equal variance. They use the term homoscedasticity because this time we're checking to see whether the variance is equal or consistent across all the values of one of the variables. I'm going to tell you what we do, then I'll run it in SPSS and then we'll talk about the output. When we go to some options, we'll click the plots button because we're going to create some plots to check our assumptions. We're going to find an option which says Z-pred and Z-resid, and we're going to plot them X against Y, and that's going to help us check for homoscedasticity. The other thing we're going to do is tick a box for histogram, which will create a histogram of our residuals, and we'll also tick normal probability plot, which will give us a QQ plot. Both of those help us check the normality of the residuals. So now I'm going to run that in SPSS, so we'll switch over to SPSS. So first thing I'm going to do is check the assumption of linearity. So I'm going to use my chart builder, which is under graphs. I'm going to choose a scatter plot from here and then click and drag this up to the empty box. And then I choose my variables. So my dependent variable goes on my y-axis and the independent variable always goes on the x-axis. So this is just a graph for me to look at to check the assumptions. Here's my graph. And what we're checking for is that there's not a relationship that is, maybe it goes up and then levels off, or where we don't want it to go up and then down, because we'd need another type of regression to check for that. We're checking that it's roughly linear. Now you can see this is messy. This doesn't really look in a straight line, but that's okay to put into a linear regression because there's nothing, no other relationship that's obvious looking at this graph. So I'm happy from this that I can put this data into a linear regression. Now what we're going to do is run the test and ask the test to check for assumptions at the same time. So to run a simple linear regression, we go to Analyze, Regression, and Linear. We put our dependent in there, so ours is our exam score. The number of hours is our independent. And then we've got some options to click on. So I'm going to click on Plots, and then this is this Z-pred and Z-resid here from the list. These are predicted values and residuals, so numbers that are generated while it's running the test. Let's put Z-pred into the x-axis and z-resid into the y-axis. That's me creating a plot by doing that. I also want a histogram of my residuals, and I want a QQ plot of my residuals, so I tick that box here. Click continue and OK. And what I tend to do first is finish off checking my assumptions first before I even look at the results of the regression. To do that, I'm going to scroll down. So this one checks for homoscedasticity, and what we're looking for is that there's no pattern to these dots. We don't want a funnel shape or anything. So this is what we created by putting in zpred and zresid into that option. So that looks good to me. There's nothing obvious going on there. So the next assumption I want to check is that the residuals are roughly normally distributed. And hopefully this looks familiar to you if you've checked for normal distribution on a dependent variable before. It's the exact same, but this time we're just checking it for the residuals. So you can see here there's very few that are very close to our line of best fit, and there's very few which are very far away from our line of best fit, and most of them are in the middle here. So we get this nice bell-shaped curve. The other thing that lets us check for normality of the residuals is this plot here, and all we're looking for is that the dots are roughly lying along this line. So that looks good. So that's us happy that our assumptions are met. So now what we're going to do is go to the main results of the regression. Because we're doing simple linear regression, you can ignore this first box. This second box has R squared value in it. You want to report this R squared value. It's the effect size. And you can interpret it like this. You can say that the variation in the dependent is explained by this amount, is explained by the independent. So put another way, the variation in the exam score is 18.6% of that variation in the exam score is explained by the number of hours that you study. So to explain R squared, we can express this as a percentage. So 0.186 would be expressed as 18.6%. And then we can say that 18.6% of the variation in the dependent, our exam score, is explained by our independent, the number of hours studied. The next box down is the ANOVA box. And ANOVA is telling us whether the independent significantly predicts the dependent. And what you need to do here is report certain values in the same way that you would for ANOVA. So we want this number here, which is the regression degrees of freedom. So that's number 1. We want the number 35, which is the residual degrees of freedom. We want the test statistic, which is given the letter F for ANOVA, so that's 8.007. And we want the p-value as well. So we'll come back to how you would interpret this p-value when we talk about alpha levels. Then we come on to this box here. Now, we can use the unstandardized coefficients B, and we're going to look at this number 44.977 here, and this number here, 0.445. We can do a few things with them. So what I'm going to do is explain to you what they mean in terms of the regression. Let me split my screen. So what we've got is we've got this graph, which is hours of study, and then your grade. Sorry, it's a bit squashed there. And then we've got each person as a point here. And then what the regression has done is it's drawn a line of best fit through those points. You may or may not remember from last time you studied maths that there's an equation we can use to get this graph, to get this line here. So you might remember that we can draw this line by using y equals m times x plus c. Some people learnt this as y equals ax plus b. It's the same thing, we're just using different letters. So you might have learnt it either way, or you might not be familiar with that. So what we can do with this equation is plug in these b values here into that equation, and then we've got a line that can be used to predict grade given the hours of study. So if we do that, we would get y is equal to 0.445. So I've replaced this m, or this a, depending on what you've learnt, with that number there. So the number of hours studies b. And then we would times it by x, and we would add this b here, this 44.977. And this number here is where the line of best fit crosses this axis. So it's called the intercept. It's a point which is when x equals 0. And then what we can do is we can plug in what our y and our x are. So our y is a grade and our x is the hours of study. So we can now have an equation that says something like grade equals 0.445 times the hours of study plus 44.977. And what people do is they type that onto their graph when they're reporting their regression, if they think that that's an important regression result. So that's something you might want to do. The other way that we can interpret these coefficients, the other way they're useful, is that we can take this number, this 0.445, and say that it's the number that y increases by for every 1 unit of x. So for example, if we were increasing the numbers that we study from, say, 15 to 16 hours, then the exam grade we get is going to increase by 0.445 marks. So let's recap that using the slides. We've got this output, we've got the Z-pred versus Z-resid plot. And that's because we put those values into X and Y, and that was to check for homoskedasticity. We want that plot to be random. We don't want to see a pattern or any sort of funnel pattern in it, because if it's random, we've got homoskedasticity. The variance is equal along the variable. And what we did is, this Z-pred is the regression standardized predicted values. And they're the values which are the values that lie along the line of best fit. So they're the values that are determined by that equation. And then the other one we plugged into that plot, regression standardized residuals, Z-resid, that's our data, our residuals from our data. The standardized word, that's just indicating that they've been put on a different scale. So they're sort of mathematically adjusted, if you like, just so that there means 0 and the standard deviation is 1. You don't have to worry about that too much. The other bits we got in our output is a histogram, and we got a PP plot to make sure that the residuals are normally distributed. And this is just like checking normality on a dependent variable, which you might have done for a t-test, except we're checking normality of the residuals instead. Then we looked at R squared, and we can say that R squared is the amount of variation in the dependent which is explained by the independent. So in our case, the hours of study explains 18.6% of the variation observed in exam grades. Just remember that this data is fake, so don't take any conclusions from that. This R squared is what we call an effect size. And effect size are really important to communicate to the reader how much of an effect the independent has on the dependent. Because we could have got a value which is 0.60, and that would mean that the amount that you study explains 60% of the variation in your exam grade that you get. Effect size is related to something called power. We talk about the power of a statistical test. So if there's a really large effect size, we say that the test has more power, so the regression would have more power. And that means that it's got more chance of detecting an effect if one exists. So our R squared was 18.6%, and that's fairly low. So that's quite hard for the test to detect an effect. It's got fairly low power. Whereas if the effect size was 60%, then the test would have more power because there's a closer relationship between the two variables, if you like. For the p-value, we're going to report the ANOVA F, which is the ANOVA test statistic, and we'd also report the degrees of freedom, both the regression and the residual, and we'd report our p-value. And the p-value, remember, indicates if the independent significantly predicts the dependent. Another way to think about this is that the p-value is saying that the data is close enough to that equation, i.e. the data fits that equation, that model, well enough. We're going to talk about alpha levels, which are the same as significant levels. What we did is, in my head, I had chosen an alpha level of 0.05 before the test. I tend to work with an alpha level of 0.05. Now, the lower the alpha level, so let's say that we could have chosen 0.001, if we'd chosen that, we would have been less willing to reject a null hypothesis. And that would have meant that this lower alpha level would have reduced our chance of making what's called a type 1 error. So a type 1 error is made when you say there is an association, that there is a significant association, when in reality there isn't. So you reject that null hypothesis, but that's a mistake you shouldn't have done. Now if we look at our example, the p-value for hours of revision was 0.008. And that's a good example of why that choice of alpha level is really, really important. So we chose 0.05, but we could have been a bit stricter, if you like, and chosen 0.01, or we could have even chosen 0.001. Because we chose an alpha level of 0.05, it meant that we're going to conclude hours of study significantly affects exam grade. But if we had chosen an alpha level of 0.001, then we would have concluded the opposite. We would have concluded that hours of study does not significantly affect exam grade. So your choice of significance level, of alpha level, is really important. It affects your conclusions. The other piece of output we got was this beta, this B, and that's the coefficient. That can be interpreted as a change in the dependent when the independent increases by 1 unit. So for example, let's say that we increased our hours of study from, say, 20 to 21 last time. The example I used before was increasing it by 15 to 16, but it's the same situation. Then again, the exam grade would increase by 0.445 marks, in theory. And the other thing we can do with these coefficients is use them to create an equation. So here we used 0.445, which was the coefficient of our independent, along with what's called the constant coefficient in SPSS, which is the intercept. And that for us was 44.977. And we plugged that into our equation so that in theory, we've got an equation that we can use to predict the exam grade from the hours of study. So our equation looks something like this, and we could report that, or we could report it by typing it on the regression graph. So now you understand a bit about how simple linear regression works. It's easier to understand how multiple linear regression works. Multiple refers to the fact that now we've got more than one independent variable. And the linear again refers to the fact that the relationship between the dependent and some of the continuous independents is a straight line. And what you can do in multiple linear regression is that you can test for the effects of scale independent variables, so continuous independent variables, alongside nominal and ordinary ones. You can do it at the same time. So to get a data set to play with, to do multiple linear regression, go back to the VLE and we're going to open up workshop data, exam grade, but this time multiple regression. So in this data set, we've got the dependent variable here, and again, it's an exam grade. And then all the other columns here are independent. So here we've got 6 independent variables. If I go to variable view, we can see more information. You can see we've got gender here. Females are 1 and males are 2. We've got an age in years. We've got distance travelled, distance uni, which is the distance travelled from term time address to university. Again, we've got this hours of study, which we had in our previous example data set. We've got a previous exam grade, which is the grade from the last exam the student's at. And we've got a grade average, so a mean grade from other exams as a percentage. And this is our dependent here. What we're going to do in SPSS is we'll run a multiple regression and test some of the assumptions at the same time. And then we'll look at the output of the multiple regression. These are some of the options that we're going to do in SPSS. So again, I'll run through them here, I'll show you them in SPSS, and then we'll talk about them after. So one of the options is by clicking on the statistics button, and we tick something called descriptives. That's going to help us check something called multi-collinearity, which I'll talk about next. The other thing we can tick is collinearity diagnostics. That checks the same thing. We're checking this assumption of multicollinearity. Then, just like we did for the simple regression, we're going to click on plots and tick histogram Again, that will test the normality of residuals. And again, we'll tick normal probability plots, which also tests for the normality of residuals. Then what we're going to do is tick something called produce all partial plots. And what that does is test for the linearity between each independent variable, or each scale independent variable at least, and the dependent variable. So we did that in our simple linear regression by using the chart editor and actually drawing a graph. This time we can ask it to do it for us, draw these plots for us. And then the other thing we're going to do, is click on save. Now this is going to save some numbers for us, as in it's going to create, add 2 extra columns in our data set. We're going to ask it to save the unstandardized, which is under predicted values and pre-1. Then we're going to tick studentized, which is under residuals, which is SRE_1. And the reason we're going to save these 2 columns of data is so that we can create a graph to check for linearity. Let's run that in SPSS. So let's look at some of the assumptions by going to a resource online. You can use any resource. There's lots of really good books as well. I'm just going to use a layered resource, and I'm going to type in multiple regression. Here we get a guide, and it tells us about multiple regression. And then it's got some assumptions. So it lists the assumption of multiple regression. And I'm just going to draw your attention to some of them, which are a bit more complicated. So assumption 4 is that there needs to be a linear relationship, but that linear relationship needs to be between the dependent variable and each of the independent variables. So we have to check each one in turn. But there also needs to be a linear relationship between the dependent variable and the independent variables collectively. So we're going to check that as well. Then the other assumption is homoscedasticity, which is what we checked in when we ran the simple linear regression. So that's that one there. And then assumption 6 is this thing which we mentioned earlier, which is multicollinearity. So that's when we have 2 independent variables that correlate with each other. And that's a problem because they're effectively a measure, they can often be a measure of the same thing, not necessarily, but statistically that's not very good for the regression model. So we want to know whether any of our independent variables correlate with any of the other independent variables. The other one that is we might not be used to is this one, which we had for our simple linear regression as well. It's whether those residuals are normally distributed or not. So again, we're going to check that just as we did for simple linear regression. Let's do that in SPSS. So to run a multiple regression, we go to Analyze, Regression, and Linear again. So again, we put our exam score in dependent, but this time we're going to put all of these in, and if you want to do it all at the same time, just hold down Shift. So we put all our independents under that independence box. And now we're going to use the options down here. So if we click on statistics, we're going to tick this box here which says descriptives, and we're also going to click collinearity diagnostics. Both of these will allow us to test that assumption of collinearity. Then we're going to click on plots like we did for the simple linear regression. And we're going to click histogram to check the normality of residuals. And then click normal probability plot so that we get PP plots of values versus residuals, again to test for normality. And because we're doing multiple linear regression, we want to check this assumption that all independent variables that are scale have a linear relationship with the dependent variables. So we're going to click produce all partial plots. Next, we're going to click save. And under the predicted values, we're going to click unstandardized. That's going to create a column which has the name pre_1. That's what we're doing there. And then under our residuals, we're going to click studentized. That'll create a column in our data set called SRE_1. And we're going to do that so that we can create a graph to check for linearity. Continue. And OK. And before we look at the output, I'll just show you that we've got these two extra columns, this pre_1 and this SRE_1. I'll look at my slides at the same time as looking at SPSS now, so I'll split my screen. So the first thing we're going to do is finish off checking the assumptions. So the first assumption we're going to check is linearity. So we want to check that there's linearity between the dependent variable and each of the independent variables. We're going to do that by looking at the partial regression plots, which are down the bottom. Here we go. So this is the first one, but it's gender, so we can ignore that one. This one, we've got age against the exam score. And we can see that there's maybe not a linear relationship, but there's certainly not anything else going on. So that's okay to put that into the regression. We've got distance from term time address. Again, there's nothing funny going on there. There's certainly not a relationship that's this shape or levels off or anything. Then we've got, sorry, it keeps jumping, the number of hours students reported studying and the exam score, that looks okay. And then we've got the grade from the latest exam. Again, that looks fine. And the mean grade from all other exams. And again, there's no other shape in there, so we're okay to put this into a linear regression. Now what we're going to do is check for linearity between the dependent variable and all of the independent variables collectively, and check for homoscedasticity. So we're going to create a plot, a scatter plot of these two columns that have been added to our data set. So this pre_1 and SRE_1, we're going to create a graph. So to do that, we go to graph in Chart Builder. We choose Scatter Dot and choose the first one. We just want a simple scatter plot. And we see here we've got the last two columns we're going to put onto our graph. Click OK. Whoops, daisy. So here we can see in this plot that if we've got a band of points, then we can say that we've got linearity between the dependent variable and all the independents collectively. Also, if the points are in a random pattern, we've met the assumption of homoscedasticity, i.e. that variance doesn't vary, it's roughly random, it's roughly equal as we go along the line. It's not really small for higher values and really big for smaller values, let's say. The next assumption we're going to talk about is multicollinearity. So that's when two independents are highly correlated, and it sometimes happens if two independents measure the same thing. So to check for that, for multicollinearity, we're going to look under the correlations table. So if we scroll up to there, here we are. So I'll just put this full screen, I think. So all this is each of the independent variables correlated against each of the other independent variables. And we've got our R values here, so our Pearson's correlation coefficients here. Then we've got our P values here, and we've got just N on the bottom of the table there. It's all 37. And what we want to check is that none of these R values are over about 0.7. 0.7 is roughly a benchmark. So we can ignore the ones going diagonal because that's just a correlation of the independent against itself. But if we look at some of these values, these look okay until we get to here. Here we've got the grade from the latest exam and the exam score in the subject out of 100. Oh, that's our dependent actually. So we can ignore this column. Let's look at the next column. They're fine. There's nothing over 7 there. There's maybe distance travelled from term time address to age and years. That's correlating, but I can't see a reason why the age and distance travelled would be measuring the same thing. So I'm not sure whether that really is collinearity or not. We've got 0.06, 0.12. We're just checking these ones. Oh, and there we've got 0.9. So that's definitely over 0.7. That one is the mean grade from other exams and the grade from the latest exam. So you can imagine they probably are measuring the same thing. They're measuring the academic ability of the student. So I would say, yeah, that's beginning to look like I do have a multicollinearity problem there. The other way I can assess multicollinearity is by looking at something called the VIF values. Let me find them. Here we go. Under the coefficients box, we've got all our independents listed here, and the last column has something called VIF in it. And again, there's no hard and fast rules. I tend to go to anything that's over 5 isn't great, but other people go to anything that's over 10 isn't great. So it really there's no rule that everyone agrees upon. But here you can see we had a 0.7 R value for our age and our distance travelled. We have the VIF values too. So that's confirming to me, yeah, that's not a big problem, age and distance travelled. Whereas if I look down at the grade from the latest exam and the mean grade from other exams, then they're over 5. So I'm not too happy about those two independents being in the same multiple regression. So what I'm going to do is rerun the whole multiple regression analysis and remove one of these. So I've got to make a choice between what one I remove. Because this one encompasses all of our exams, I'm going to keep that in as a better measure of academic ability, and I'm going to remove the grade from the latest exam. I can do that using my recall button. And under my independence, I'll just remove that from the analysis. All these settings should be the same. So there we've seen to check for multicollinearity, look under the correlations table. Make sure there's no correlation coefficient, i.e. no R value that's over 0.5. And you can also look at the VIF values under the coefficients to make sure that no VIF is over 5. Sorry, make sure no R value is over 0.7, I meant to say. If we've got multicollinearity, rerun the analysis excluding one of the independents. So now we're going to take a look at the output of the actual regression itself. Let's go down past our correlations. We'd probably check our correlation values again. And the first box I'm going to look at is this model summary. We've got our R squared here and our adjusted R squared. Now, adjusted R squared is adjusted so that it's more realistic to what would happen in the real population. So when it comes to multiple regression, we're better using the adjusted R squared in our reporting. So here ours is 0.576. So that means that all the independents together are explaining 57.6% of the variation in our dependent in our exam score. So we can report that value. And then just like the simple linear regression, we've got an ANOVA table, and that's saying that whether all these independents collectively significantly predict the dependent. Again, we would report the regression degrees of freedom, the residual degrees of freedom, the F statistic, and our p-value, which is under sig. Then when we scroll down to our coefficients, you can see this looks bigger than it did in the simple linear regression because we've got all these independent variables listed here. So the way to tell which of these independent variables has a significant effect on the dependent variable is to look at the p-value, which is under sig. So you can see gender's bigger than 0.05, age is bigger than 0.05, so is distance travelled, so that has no effect. We can see number of hours a student studying is just above 0.05. So we're going to conclude that, again, that has no significant effect. Whereas the mean grade from other exams, that does have a significant effect. That's a significant p-value there. So we'd probably want to report these p-values in this column here to tell our reader which of the independents is significantly related to the dependent. Again, we can use these coefficients, this b, to say what the change is in the dependent when the independent is changed by 1 unit. So let's just say we can only really do this for the significant independence. So let's do it for mean grade from other exams. Let's say that the mean average grade from other exams increased by 1%. So it was 50 instead of 49%. That would mean in theory that the mark for this exam would increase by 0.914 marks. Now, to interpret what B means for categorical independent variables such as gender, it's a little bit different. Our gender here isn't significant, but if it was, the way we think about it is that we're changing from 1 to 2 for our gender. So 1 is female and 2 is male. So an increase from female to male, so this change between 1 and 2, means that the exam grade would increase by 2.008 if it was significant, but it's not. So we're going to use another example on the slides to talk about that. Then we can use all of these values in the very similar way that we did for our simple linear regression to get an equation that could be used to predict exam grade. Now, you might not want to do this because all of these aren't significant, but in theory, this is the equation of the regression that we've just ran. So let me just draw that for you. Right, so here's our B values here. And the equation is going to be something like our Y value, which is the exam grade. That's the thing we're trying to predict. That's going to equal this value here, so 2.008 times gender, plus the next value, which is age, so 0.289 times age, plus, that would actually be minus 0.106. That's because this value here is minus, times the distance travelled to uni. The next one's plus. Number of hours student reported studying, 0.226 times hours. And then plus 0.914 times mean grade of our exams. And at the end, we're going to add our intercept, which is this constant B. So it's minus value, so we write minus 8.765, and that would be the equation that you might want to report. So it's best to use R squared adjusted rather than R squared for multiple regression. And as with simple regression, we're going to report the ANOVA F value, the ANOVA degrees of freedom, and the P values. We want to look at the T values and the P values for each of these independents. So we might want to report the T values as well as the P values. And then just like simple regression, we can use these B values, these coefficients, to make an equation. Now, just to say, that's not necessarily what we call an optimal model, because there's a lot of independents in here that don't have a significant effect on the dependent. So you then get into the process of rerunning the model without the significant independence to try and find the best model the model that would fit the data best and predict that dependent variable. Just a note on type 2 errors. A type 2 error is when you accept a null hypothesis when you shouldn't have done that. So you've accepted, let's say, that there's no effect of the hours that a student studies on the dependent, which is the exam grade. So in our results, we're going to accept this null hypothesis that there's no effect of hours of study on exam grades. But you might want to ask yourself, well, does this agree with other research? And if you're really interested, there's a nice paper here by Nonis and Hudson, which I've given you a link to just in case you've been thinking about this. What we would want to have a discussion on is whether we've made a type 2 error. And we'd want to consider, is this because of the analysis we've used, or is it true? And the reason I say that is because the number of hours students reported studying is the exact same data as we used in our simple linear regression, where we did find a significant effect of the number of hours people were studying on their exam grade. But when we put it into multiple regression, that effect, if you like, disappears. So our conclusion is affected by the analysis that we use, and you need to be aware of that. You need to be aware of how conclusions and significance can change based on how you do your analysis. The last regression we're going to look at is logistic regression. Some people call this binomial regression. Other people call it binary regression. You can have binomial logistic regression. They're all referring to roughly the same type of analysis. So don't be confused by the terminology. Logistic regression can also refer to multinomial logistic regression, but usually that's got multinomial in the front of it. So this time, logistic regression is when your dependent variable is nominal and there's only two categories of that. So in other words, your dependent variable is binary. Some people call this dichotomous. So examples of that would be if you have a dependent variable which is people answering yes or no in a questionnaire. We're going to use the example where people have passed or failed an exam. So it's categorical, there's only two options. Or you might have something which is an animal male or female, and we've only got two options there. If you're going to use logistic regression, please do have a look at someone else's explanation of it to try and understand it. It is a little bit more complex. So study beyond this session if you're using it. So the dataset we're going to work with is on the VLE. It's called Workshop Data Exam Grade Logistic Regression. Let me make the screen bigger. And here you can see we've got a dependent variable in this column, and all of these five are the independent variables. What we've done here is we've coded people up as either passing, so those people get a 1, or failing, so those people that fail have got a 0. And the independent variables are the same as the last example, just to make it easy for you. We've got gender, age, the distance that someone travels to uni, the hours of study that they've put in, and their previous grade. So this is we're going to give you a brief explanation of how to check for linearity. It is a little bit complicated, so I'd advise that you look at how to do this in SPSS at another source, such as a book or a website. And once we've explained that, the theory of it, in SPSS, we're then going to show you how you would run a logistic regression, and we'll have a look at the output. Then we'll consider power, and we'll look at odds ratio. So one of the assumptions of logistic regression is that there's linearity between the dependent variable and any of the scale independent variables. But if you think about it, getting linearity between the dependent variable when it is binary isn't really possible, and I'll show you that with a diagram. So here, if you imagine, where would it? If you imagine we've got our an independent along here. Let's say it's the mean grade from previous exams. And then along here we've got our dependent. But this time it's whether you pass or fail the exam. But because it's binary, we just have fail here and pass here. And so when we plotted these against each other, we would just get the lines in two lines. So we would have a line of dots here for fail and a line of dots here for pass. So we can't really test for linearity between this independent and the dependent. So what this assumption is, instead, is it's checking for linearity between the logit transformation of this dependent variable, this binary variable, and any of the scale independent variables. So to do that, to check that assumption in SPSS, we use what's called Box-Tidwell procedure. It's quite involved and it's quite lengthy, so I'm just going to summarize it here. And if you need to do a logistic regression, please do look this up. So just briefly, what you would do is create new columns of data, which are the log, or natural log, of all of your independent variables. Then what you would do is run the logistic regression, including combinations of the variable with its log version. So you sort of times this variable with the log version, and you put that in as an independent. And then you get output here, and you read off this table, you're looking at some p-values. So this is explained in Andy Field's 2018 book, so Statistical Analyses in SPSS. It's also explained in the layered advanced resources, so those are ones that unfortunately you have to pay for. It's also explained in other websites as well. Just Google Box-Tidwell procedure in SPSS for logistic regression. The other assumptions that logistic regression have are that you can't have any multi-collinearity. So we talked about that in multiple regression. And also that you can't have any outliers or influential points. So what we're going to do in SPSS is choose some options. The options we're going to choose are something called Hosmer and Lemischau, and that's going to test for model fit. So how well our data fits this equation, this model that the test comes up with. And then we're also going to tick a box for case-wise listing of residuals. And that's going to make sure that we've got no outliers. We don't want any outliers that will really drive the significance of the test unfairly, that sort of influence it unfairly. So let's run that in SPSS. Let's go down to SPSS. To run a logistic regression, we go to Analyze, Regression, and it's under binary logistic. We put in our dependent, which is whether our student passes or not. This is our binary dependent. And then we put all our independents in to the covariates box. Then we have to tell it that this gender independent isn't a scale variable, but it's nominal, so it's categorical. To do that, we click on categorical and we select gender so that it knows which is which. I'll just point out to you here that it gives you a choice of choosing what's called the reference category. So it's saying that the reference category just now is set to last. So that means that I think our males are number 2 and our females are number 1. So 2 is our last category. It's going to use that as the reference category, and I'll come back to explaining that. Then we're going to go to the options button, and we're going to tick this Hosmer and Limashow goodness of fit box here. And also we've got case-wise listing of residuals, just to check for outliers. It's going to give us a table listing the outliers. And then we'll click continue and click OK to run that test. Let's make the output bigger. So first of all, I'm going to finish checking the assumptions, as I usually do. The first assumption I'm going to look at is to see whether there's any outliers in my data. So to do that, I'll scroll right the way down to the bottom and look at this table. Now, I don't have a table here, and it says the case-wise plot is not produced because there's no outliers, like no outliers were found. So that's a good thing in this example. If we go up to the top of the output, let's see. Here we go. We've got a summary of codes. So this is how it's coded up the dependent variable. In fact, we coded it as 0 and 1, and they've kept that coding. We've got a summary of sample sizes. So it's just said that it included 37 cases in the analysis. We didn't have any missing cases in our analysis. And it's telling us for our nominal independence, it gives us a summary of how many females we had and how many males we had. Then we've got, you can think of this in 2 sections. We've got something called block 0 beginning block. And then we've got block 1 method equals enter, right? Okay, so we've got block 0 and block 1. You might have heard of null models. That's the same as block 0 in SPSS. So a null model is a model, except it doesn't have any independence in it. It's a bit of a strange concept if you've not came across it before. It's like creating a model where you're only modeling the dependent variable. Whereas the block 1 model is the actual model which has all the independent variables included in it. So what you can see in this classification table in our block 0, our null model, is that these are the observed values, these 0 ones, and this is the predicted values. And it's made a crosstabs table of the observed against how it's predicted. And what it's done is it said those there were 4 students that failed, and when it came to predicting how those students, what those students' grade was, what their outcome was, the null model has predicted them as a pass. So it's predicted them wrong. And you can see that here with percentage correct where it says 0. The people who passed, it's done better. It predicted that all 33 would pass, so it was 100% correct there, but it's wrong here. So that's the null model. If we compare that to the actual model, the block 1 model, here we go. Here's the classification table here. Now you can see that when we have our independence in our model, it's able to predict things much better. So these students who failed had a 0 value. It predicted correctly that those were the students who failed. And same again, the students that passed, it again predicted them correctly. So it had 100% prediction rate, this model. So what we have in our output is an omnibus test of model coefficients. So this is under our block 1. And this is going to tell us how well the model predicts the dependent compared to the null. So if this value is significant, so I'm going to look at the model part down here, and I'm looking at this p-value here. If the model is that p-value is significant, then it's indicating that the model is a better fit than the null model, just as we've seen by looking at the classification table. And then we can look down here at the Hosmer and Limashow test. Now that kind of does the same thing, except we interpret it in the opposite way. What I mean by that is if the p-value is not significant, that indicates that there's the model is a good fit. So you have to kind of be on the ball on how you interpret the output here. The other thing we've got here is what's called, these are pseudo R-squareds. So in a logistic regression, we can't get an R-squared effect size because the mass is just a bit different. So some people have came up with ways of coming up with an effect size. They've called it R-squared, but it's not really an R-squared, so they call it a pseudo R-squared. So you've got Cox and Snell R-squared, and then someone else has came up with a different way of coming up with a pseudo R-squared called Nagel-Kirke. Never know if I pronounced that right. So you can report one of these. Whatever one you report, just write that you're reporting that version of the R-squared. Let's see what else we've got. Want to go down to variables in the equation table. So here we've got all the independent variables listed. And then we've got p-values here which indicate which of the independents are statistically significant. Now, interestingly, these p-values are all non-significant. And what that's indicating to me is that the test just isn't willing to say that one of these is useful in predicting the dependent and predicting whether someone passes or fails. And we'll talk about why that might be in a minute. The other thing we've got is this end column. This is the odds ratio. So this EXPB, that's the odds ratio. Our beta value here, our B here, is the log odds. And we'll talk about the difference between those two when we go back to the slides. So just to recap what we've done, we finished checking the assumption that we have no outliers by looking at that table, but we didn't have any. So that's at the end of the output, this case-wise list table. The block 0 is our null model and block 1 is our actual model. Our omnibus tests, our Hosmer and Limashow, and our classification table, they're all about assessing how well the model predicts the dependent variable. And then we've got this pseudo R squared. We've got two versions of it. You can choose what one you want to report. Just whatever you choose, just write down the name of it. And then we've got p-values in variables in the equation box, and that gives statistical significance for each of these independent variables. So let's talk about why some of those independent variables might not have been significant. We need to do that, we need to think about the power of a test and the sample size. So the power of a test is how likely it is to detect an effect if one exists. And we like tests that have more power because that means that we're less likely to make a type 2 error. So a type 2 error is when you say that there's no effect of an independent on dependent, when in reality there actually is. So we would conclude someone's previous grade wouldn't predict whether they pass or fail this exam, when actually in reality it does. Now, power of a test is really strongly affected by sample size, and that the bigger the sample, the easier it is for a test to come up with the correct answer. Correct answer as in not making a type 1 or type 2 error. So let's think about this example. Our total sample size was n equals 37. But that's kind of misleading thinking about it like that. Because actually what we had is a sample size of 33 for students who passed and a sample size of only 4 for people who failed. We only had 4 fails. So there's only 4 respondents that failed that exam. That means that the test might not have had enough power to conclude which independents predict the dependent. So it doesn't have enough information, if you like, to predict who is going to pass the exam and who failed the exam. So my question here would be, is my model really reliable if I'm working with that number of samples, only 4? We had two measures in our variables and equation table. We had something called odds ratio, which is our EXPB, which I think is easier to report than the log odds, which is under B. Both of these are given under that variables and equation table. So what we use these for is to quantify the association between the independent and the dependent. So to say if the independent changes in a certain way, how does that affect the dependent? Now, in our data, all of our independents are not significant because we've only got n equals 4 for our fail, so our model's not that good. So we shouldn't even look at our odds ratios. They're just really misleading. We shouldn't really report them because none of our independents are significant. So what I've done is I've taken other examples, which are on the next slide, to give you an idea of how to interpret these numbers, because it can be difficult to get your head around. So we're going to talk about how you interpret odds ratios for a nominal variable such as gender, and then we're going to talk about how we interpret odds ratios for a scale variable such as previous grade. So for our gender, we had 1s equals females and 2 equals males. So when we put in our gender independent and we told it that it was a category, I pointed out to you that you had this reference category last and first. this is where that comes into it. So the reference category is the last. So the reference category is set to males. So what's happening is that we compare females to males. If our p-value was significant, let's just pretend it was, and let's just pretend that our odds ratio, so the number under EXPB for gender was, I've made this up, 1.245, then we could report it like this. We could say females are 1.234 times more likely to pass the exam than males. Just a reminder here, my data is completely fake. I'm not saying there is a gender difference in pass rates in exams. But you can use that sort of template if you've got a categorical independent. Now, if we've got a scale independent variable, let's just pretend it is previous grade. Let's just pretend that our p-value had been significant. And let's pretend that our odds ratio, our EXPB for that independent was 4.321. I've made it up. Then we could report it in this way. An increase of 1 in the previous grade means that odds of passing increases by 4.321. So I'm just going to try and recap some types of regression to try and help you doing regression in SPSS. If we had simple and multiple regression, so this is the first two types of regression we did, our dependent is always scale data. If we have dependent as binary, so it's yes or no or 0 or 1, then we're doing a binary logistic regression. So those are the three types of regression that we've covered in this workshop. Now, if you had a dependent which was ordinal in its nature, so it was categorical, but those categories had an obvious order. An example here is Likert data, which where the data points can only be 1, 2, 3, 4, or 5. Then we would do an ordinal logistic regression. If we had a dependent variable which had nominal categories, so here we've got multiple nominal categories, not just two. So let's just say that our dependent could be red, green, blue, or yellow. Then we would do something called a multinomial regression, sometimes called a multinomial logistic regression. Sometimes we have dependent variables which are counts. So, so sometimes we have a dependent variable which are counts. So let's say we've counted the number of people that turn up to somewhere. We've counted the number of fish on a transect. If our data is counts, we should really use something called a Poisson regression. So if you needed to do one of these regressions, and they would be a bit more complex, this is how you'd go about it. I'd recommend spending time actually understanding the test itself, rather than just going to a video or instructions that tell you which menus to go in SPSS. And the reason that's important is because you're going to have to describe it in your methods section. You won't be able to do that if you don't understand the test. So use books, there's lots of websites out there, just Google, and there's some good online videos as well to research the tests. If you're in a lab, you can ask lab colleagues or your peers. You can ask supervisors if they've done that specific test in SPSS. And don't be surprised if you're watching videos, if you're looking at resources, and people are using syntax in order to run the test. It's possible that maybe the test you're trying to run is only possible in SPSS using syntax. By that I mean SPSS computer code. Here's some resources. So I've used Laird website. I think they have nice clear SPSS guides. There's also some nice videos and written guides on a website called StatsTutor that are free for anyone to use. And we have Andy Field's book. I think I I didn't give it its proper title earlier. It's Discovering Statistics Using IBM SPSS. It's in its 5th edition now, but the 4th editions are still good to get the concepts from. If you don't like Andy Field because he has quite a lot of jokes in his books, you want something that's a bit more straightforward and to the point, then Julie Palin's SPSS Survival Manual is a good book.